Every model you have ever shipped was fallible. Even when point predictions were correct, they were incomplete the moment a decision depended on an internal confidence score. Standard API outputs, specifically the predict proba function in scikit-learn and softmax layers in deep learning, are widely misinterpreted as true probabilities. Technically, these numbers are uncalibrated class scores dressed in probabilities clothing. They may sum to 1, but they carry no guarantee that a 90% claim will actually result in 90% accuracy. High top-line performance metrics, like accuracy and AUC, routinely mask severe internal miscalibration. These metrics provide a summary of the dataset, but stay silent about individual prediction reliability. A model can pass every standard evaluation screen your team applies while being dangerously wrong about its own certainty. Accuracy filters out the wreckage, but it cannot certify the survivors. We need a framework that can be audited and defended. To see this discrepancy in a real environment, we can audit a credit card dataset containing 30,000 clients scored for default risk. This chart compares a gradient-boosted tree and a tuned neural network. On standard metrics, they appear virtually identical, tied at 81% accuracy. But the audit reveals a failure in the neural network's highest confidence bin. It claimed a 93% probability of default, yet the actual observed rate was only 70.4%. For a bank, pricing risk on that false confidence leads to a $0.7 million recurring loss in a single modest loan book. The model is overstated where it shouts and understated where it whispers. Standard evaluation metrics remain silent about this 23-point overstatement. Only the audit, checking a promise against its delivery, separates an honest model from a fabulist. Conformal prediction provides a rigorous alternative. It wraps around any existing model to generate a set of predictions that contains the true label at a specified error rate. The mathematics underneath are not recent heuristics. They are the product of an intellectual line moving from Kolmogorov's theory of randomness to formal, provable theorems. The core promise is exact marginal coverage at any finite sample size. The guarantee is as firm at 500 calibration points as it is at 5 million. This holds as long as you meet one assumption: exchangeability. Your calibration data must be a symmetric peer to the future data you predict on. We can visualize this on the D1 synthetic dataset. While class 0 is isolated and easy to predict, classes 1 and 2 overlap, creating a hard region where uncertainty is unavoidable. We are trading the false certainty of point predictions for mathematically honest sets. The implementation logic follows 4 verbs: split, score, quantile, and predict. To score, we measure how strange a label looks to the trained model. A high nonconformity score means the model is surprised by the outcome. The quantile step is where the mathematical guarantee is fixed. We find the score threshold that captures a specific share of the calibration data. This logic requires a finite sample correction. We calculate the rank using n+1, not the raw count of the calibration set. That +1 represents treating the new test point as part of the calibration bag. Finally, to predict, we include every class whose strangeness falls below that threshold. The implementation is transparent, collapsing complex model internals into a single numerical comparison. Consider a tiny calibration set of only 9 numbers. For a 95% guarantee, the required rank becomes 10. Because the rank is greater than the number of available scores, the threshold becomes infinity. In this scenario, the model must include every possible label, because it cannot certify the guarantee with only 9 points. The method degrades honestly. It tells the user it lacks the data to be certain, rather than guessing. Returning to our D1 feature map, we can see the resulting conformal output. In the isolated class 0 region, the model produces a set of size 1. In the overlap zone, it returns a set of size 2, reflecting honest uncertainty. An outlier results in an empty set, stating none of its known labels clear the bar. The size of the set is the honesty: small where known, large or empty where unknown. Our final audit verifies the result. Against a target of 90%, we measured 90.2% coverage. This discipline of measuring every claim against data, using seeded scripts and held-out audits, is central to the framework. This methodology follows the standards of the school that built the theory at Royal Holloway. Uncertainty quantification is not a mathematical curiosity. It is a requirement for professional machine learning. This honesty is the bridge between a model that works in a notebook and a system you can defend in production.